Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE-222 microprocessor systems. This is your first lecture of week 12, lecture number 34, and in this lecture we are going to discuss what are timers, how many timers are there in PKT F4550, what is their difference with counters, and so on. So in this lecture we are going to target your CLO 5. In CLO 5 we are supposed to start making programs for real-life applications using the internal and external peripherals for PKT in microcontroller, and this particular CLO is mapped to C4 in Bloom's taxonomy, that is analysis and design. So in this part of your course will target on design of codes for certain applications using the internal and external peripherals. So let's start our lecture, and we'll first discuss what are timers. So let's see what exactly is a timer. All of you are already familiar with what is a counter. A counter is a simple register. It can be of any size. It can be 8-bit, 16-bit or whatever size. So it's a register and it has a clock input. It has an input for increment, that is, this is optional. Then it has an input of enable, or you can say start stop, and it may have a flag, an output of, I would represent it with an arrow, outgoing arrow. It may have a flag showing the counter full. So this is a counter. Now if in a counter, if there is a clock and we give a pulse on the increment input, the counter will count up. It will count 1, 1 plus 1 plus 1 and so on. And there may be an up down counter, so that down counter will have an additional input of decrement. Right now we are only discussing up counters. What if I change this, I want to change this counter to a timer? They are effectively the same thing. So what I have to do is, there will be no increment pin. There will be just an enable or a start stop pin. There will be a clock pin and there will be a flag that will represent that the timer or counter is full. So I don't have to give an additional pulse on this pin, on the increment pin. Whenever there is a transition of the clock, the timer will count up. So now what differentiates between a timer and a counter in PKT is the source of this clock, from where this clock is coming. So in case of counter, we have an external clock, and in case of a timer, we have an internal clock. So the clock source will differentiate between whether this register will act as a counter or a timer. So what do we mean by an external clock? External clock means that this clock will be given at an input output pin, IO pin. The physical pin will act as a clock source. We will we can attach a push button to that, we can attach a sensor to that, we can attach even a clock source to that, and whenever a transition occurs at this input output pin, a pulse will be given to this clock pin, and this register will count up. When it will count up? Only when it is enabled. So if it is not enabled, no matter how many pulses come on this pin, this clock pin, the timer will not count up or down. So in this mode, the register will act as a counter, but it will act as a timer when the source is internal, the clock source is internal. What do we mean by an internal clock source? The system clock. System clock will be used as an input to this clock pin of this register. So now there is no sensor or there is no switch connected to this pin. There is a continuous clock pulse. This will be like a periodic clock in case of timer, and in case of counter usually it is some sort of aperiodic pulses. So we are counting some events in this case, and we are using it as a timer, a continuous timer, a periodic timer in this case. So they are effectively the same. We just have to select which is the clock source. So now your PIC microcontroller, PIC-4550, it has 4 timers: timer 0, 1, 2 and 3. Starting with timer 0. Timer 0 module in PIC-4550 can operate in both 8 and 16-bit modes. So I can use it as an 8-bit timer, or I can use it as an 8-bit counter, or also I can use it as a 16-bit timer or a 16-bit counter. So this microcontroller is 8-bit. All the data in this microcontroller is of 8-bit size. So how can a timer act as a 16-bit register? Obviously 2 different 8-bit locations will be combined together and they will act as a single 16-bit register. So the count will start from 0, 0, 0, 0 hexadecimal, and the count will go up to F, 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 F hexadecimal, FF in one register and FF in other register. So there will be a least significant register and a most significant register, and they will be concatenated together to form a 16-bit register. There are certain different special function registers associated with timer module, timer 0 module specifically. They include the timer control register, timer status register and so on. So what do these SFRs contain are some bits, some control bits and some status bits. The control bits to select between different modes of operation of the timer. As we just discussed that we can operate it in an 8-bit or a 16-bit mode. So we have to select which mode we are going to use, and how to select that? We will have to give some value to certain selection bits in some special function registers associated with this particular timer. Then we have to start or stop the timer. Then we have a flag that shows that whether the timer is full or not, and so on. And also from where the clock is coming. So whether to use it as a timer or whether to use it as a counter, we have to select that also. So all these selection control bits and the flags, they are inside some special function registers associated with this specific timer. So let's take a look at the special function registers of this timer. The first SFR associated with timer 0 is the T0 timer 0 con control register. T0 con timer 0 control register. And inside this 8-bit register there are certain bits. The bit 7 is TMR0 on. So timer 0 on. This bit will turn the timer on or off. So it will enable the timer or disable the timer. If this bit is disabled, no matter how many pulses are there on the clock source, the timer will not count or the timer will not increment. So this is the effectively start stop bit of the timer. Then we have T0 8-bit. Timer 0 8-bit mode selection bit. So if this bit is 1, the timer will act as an 8-bit timer counter, and if it is 0, the timer will be configured as a 16-bit timer or counter. Then we have T0 CS, timer 0 clock source bit. So if this is 1, the transition on T0 CK 1 pin, that is one of the input output pins. Let me check that which input output pin does this represent. Okay, let's go to the, this is page 127. So let's go to the pin diagrams. In a 40 pin PDIP package, we can find it here that the T0 CKL is associated with pin number 6 RA4. So if we want to use it as a counter, the clock will be given on that external pin, and that external pin will be RA4. But if we want to use it as a timer, we will set this T0CS, the clock source bit, timer 0 clock source bit, to 0, and the internal instruction cycle clock will act as the source of the clock input for timer 0, and it will automatically increment periodically after each instruction cycle. Now this word instruction cycle should be very carefully understood. In the initial lectures related to PIC microcontroller, we came to know that each instruction cycle in PIC microcontroller takes 4 clock cycles. So this timer, when it is in a timer mode, the pulse will be provided to the timer after 4 clock cycles, 1 instruction cycle. This means that if your crystal frequency is 4 MHz, the clock frequency for timer will be automatically divided by 4, and it will be only 1 MHz. Then we have the T0SE, timer 0 source edge select bit. So this is basically for the counter mode operation of the timer, whether we want to increment the counter when we have a high to low transition or a low to high transition on the external pin. So it depends upon the sensor. If the sensor is normally high, we want to detect the change as soon as it goes to low. So we want to count it or increment the counter on a high to low transition. Otherwise we want to use a low to high transition in the opposite case. So this bit 4 is related to the counter operation. PSA, timer 0 prescaler assignment bit. Now what is a prescaler? Let me tell you, let me show you before moving on. So this is a timer, whatever clocks or input outputs there are, and this is the clock source. Now this clock is coming from somewhere. There are multiple sources from where this clock can come. This can come from RA4 in case of counter. This can come from internal crystal divided by 4, and it can come from some other XYZ source. We will discuss that later. And this divided by 4 is a part of this clock source, but there is another prescaler present here. So this is a further divider block. All the clock sources that are connected to this timer pass through this divider block, and this divider block is a prescaler. So for example, our crystal frequency was 4 MHz. So one instruction cycle will be equal to 1 MHz. So this will be the frequency that is coming at this particular point. If we use a prescaler, and if we use a prescaler of, let's say 10, the frequency will be further divided to, frequency will be equal to 0.1 megahertz. That will be here the input frequency of the timer. So why do we want to decrease this frequency? Why don't we just use this 4 megahertz or 1 megahertz? Usually the timers are used to generate delays, or the timers are used to generate waveforms. And if we see here that the timer will increment at each clock pulse, that is coming at this point. So the frequency of this clock will affect the time taken for one increment. If the clock frequency is 1 megahertz, the time taken for one increment will be 1 microsecond. So after each microsecond, the timer will increment. But in this case, if we use a prescaler of 10, after each 10 microseconds, the timer will count up once. If let's say we want to create a delay of let's say the delay we want a delay of 0.1 second. 0.1 seconds mean 100,000 microseconds. So 100,000 microseconds mean, for this case, we will need a count of 100,000. But this timer can be used in 8-bit mode or a 16-bit mode, right? So in 16-bit mode, a timer can count maximum up to 65,500, but we needed a count of 100,000. So even if we count from 0 to counter full, we will not get our required delay and we will have to run this timer again. But what if I use a prescaler of 10 and now each of my count will be after 10 microseconds. So how many counts will we need now? 10,000 counts. So I will just have to run my counter or run my timer for 10,000 counts and it will give me a delay of 0.1 seconds. So I won't have to make a loop. When we are using timers, we want to use timers within the full count. Yes, it is possible to use timers and use it for a delay that is more than their full count. It is possible and it is done in some cases, but it is not preferred. It is not an efficient way. So what we do is we try to keep our count within the maximum count range of the timer. So for example, if I see here, let's say we want a delay of 0.1 seconds. Our main crystal is 4 megahertz. So 1 instruction cycle is equal to 1 microsecond or 1 megahertz. We need 100,000 microsecond delay. So we use a prescaler of 10 and a count of 10,000 will be required. Now how to count 10,000 in a timer? The most efficient way is there is a timer register TMR0. This is a TMR0 register. It is divided into TMR0H and TMR0L. So this is an 8-bit register. This is an 8-bit register. And if we remove the H and L postfixes, it will act as a 16-bit register. So in case of a 16-bit register, we can count from 0 to 65536. But if we need a count of 10,000, we can preload it. we will load TMR0 with TMR0 is equal to 55536. What will happen now when I start the timer? It will start counting from 55536, then 55537, and then up to 65536. So this will be a total of 10,000 counts. So that is an efficient way of doing this, because if I start it from 0, it will count from 0, 1, 2 and then up to 10,000. We have to stop it. So how will I know that now the 10,000 count is reached? I will have to check the value of this TMR0. So what is the purpose of using the timer then? You can use any other counter, any other general purpose register as a counter, and you can keep incrementing it. You can calculate the delay in the conventional manner, and after each line check whether this TMR0 was, or that count general purpose register counter register was 10,000 or not. So there is no purpose left for using the timer. But in this case, if we preload it with 55536, we don't have to check the status of the register. We can just check the status of the flag. So while we can write while the timer 0 interrupt flag or full flag, I will come to the interrupt later. So this is a single flag for timer 0 that will be used for interrupt also. I can write this. So is 0. So I can write while not TMR0 IF, and I can write my code inside. So I just have to check one flag, and still note that I am testing this flag manually. If I am using the while condition or if condition or whatever condition, but I have to check this flag manually. Wherever I write this this label, whenever I have to write this label in my program, this TMR0 IF label, I am doing it manually. I will do it, the microprocessor will do it automatically when there is no label existing in my program. So that label is being checked automatically at the back end of the processor. Some dedicated hardware is checking that label at the back end, and that is the case when we use the interrupts in our peripheral. So we will discuss the interrupts of timers in our next lecture. In today's lecture, we will just try to configure the timer, start, stop it, and see how it works, how the prescaler, postscaler works. But we will keep checking this TMR0 IF flag manually. So let's come back to the T0 control register. So this PSA bit, the prescaler assignment bit, that will enable or disable that prescaler block, this prescaler block, this one, whether to enable it or disable it. And then we have the last 3 bits, or you can say the first 3 bits, bit 0 to bit 2, associated with what prescaler value we need. T0 timer 0 PS0 to T0 timer 0 PS2, prescaler 0 to prescaler 2. There are 3 bits that are used to select the value of that prescaler. It's not like we can give any value to the prescaler. We cannot enter a decimal value in the prescaler. There are only 8 options to choose from. We can choose a prescaler of 256, 128, 64, 32, 16, 8, 4 and 2. Because there are only 3 bits to select from, we can have only 8 different combinations and 8 values to choose from. So they have hardwired these 8 different types of dividers in place of that prescaler box, and we can choose from any of them. So we cannot give any other value to the prescaler. So timer 0 operation is almost explained, almost clear. there is a block diagram that I would like to show you. This is the 8-bit mode of operation for timer 0. What you can see here is the T0 CKL pin, the timer 0 clock pin, and that we already checked which pin is associated with T0 CKL, RA4. Then there is exclusive OR and T0 SE, source edge selection bit. So this pin will select whether the clock coming from an external pin will be counted as a falling edge or a rising edge. Then there is F oscillator by 4. FOSC is the main clock. This FOSC is your crystal oscillator, and divided by 4 makes it one instruction cycle. And then we have this T0CS. This T0CX is the selection bit of a selection pin of this mux. So this mux will select whether the clock is coming from this external source or the clock is coming from the crystal oscillator, the internal crystal oscillator or the external crystal oscillator, the main clock source of the microcontroller. After selecting that clock, the source of the clock, there are these two options. One is the direct line, direct connection forward, and the second one is going through the programmable prescaler. And how to program this prescaler? Through these three pins, T0 PS0 to T0 PS2, and the PSA enabled disable selection bit is the selection line of this mux. So if it is 1, then no prescaler is selected and it will go directly without any further division, and if it is 0, the prescaler will be active, and whatever value we have selected through T0 PS0 to 2, it will further divide the clock by that value. Then it will sync with the internal clocks. So that is just the hardware part. We are not interested in that. So after all the divisions or the source selection, the final clock is fed to the timer 0 lower register. Now note here that this is the timer 0's lower register only, because we are talking about the 8-bit mode of operation of the timer. We can read or write this timer 0 lower register through a correct connection with our internal data bus. We can read this register and we can also write this register. And once this register is not full, once this register overflows, like it counts up from 0, 1, 2, 3 up to 255, and then if I count again, so it will roll over from 255 to 0, and that overflow condition will set this TMR0 IF flag, timer 0 interrupt flag, to inform the processor and inform the user that now the timer has completed one count and now it is overflowed. So do whatever you want when the timer was do whatever you wanted to do when the timer was supposed to overflow. So if you don't want to do anything, just don't do anything. This is the 8-bit mode of operation. Looking at the 16-bit mode of operation, it is exactly perfectly the same from this point to this point. This is 100% same. The only difference in the 16-bit mode is we now have 2 registers instead of 1 register, TMR0L and TMR0H. So the timer 0H, timer 0 higher register contains the higher byte from that 16-bit number, and the lower register contains the lower byte from that 16-bit register. And again, both of these registers, they can be read and they can be written as well. We have already discussed the prescaler, so that is covered, and we will discuss the timer 0 interrupt maybe in this lecture, maybe in the next lecture. We will see after doing an example. So these are the registers, the summary of registers associated with timer 0. TMR0L, we know that this is the lower byte of timer, and this is the TMR0H is the higher byte. Int con, this shaded portion if you can see here is not associated with timer, and the non-shaded portion is associated with timer 0. So in int con, the global interrupt enable obviously we need for using the timer interrupt. Peripheral interrupt enable we also need, timer 0 interrupt enable we also need, and timer 0 interrupt flag we also need to use the timer interrupt. So the other bits are not associated with timer. And the int con 2, there is the timer 0 interrupt priority that we are not going to use in this course. And then we have T0 con, timer 0 control register, that we just discussed, all the 8 bits of this register. And then we have tris A, where we know that the RF4 is associated with T0 CKL, the timer 0 external clock. That is actually the counter mode of that timer. So now we know the basic registers and basic pins associated with timer 0. So let's start with an example program. We will do this same example where we have a crystal frequency of 4 megahertz, and we will have to make a delay of 0.1 seconds, or maybe we can say 0.3 seconds. We have to make a delay of 0.3 seconds, and we have to use timer 0 for that. So where this display delay will be displayed at pin RD0. So we will blink an LED that is attached to the port RD0 of this microcontroller with a delay of 0.3 seconds. So let's start making this program. The configuration file will remain the same. Delay subroutine will be there. We will remove all these variables and start our program with our main loop. So in the main loop, we only have to define one output, and then we should jump to the while one loop that will continue to keep blinking this LED. So inside this while one loop, now we want to blink this LED with a fixed delay of 0.3 seconds. So as the delay is fixed, we will modify this delay subroutine here also. But first, let's do the initialization of the various pins, the special function registers, the status pins, and so on. We are going to use timer 0, and we want to turn on or off the timer when required. We want to use the timer in 8-bit mode, 16-bit mode. So TMR0 on will be 0. Initially the timer will be off. This second bit will also be 0. It will be configured as a 16-bit timer. Then the clock's source will be internal clock. So again 0. T0 SE is don't care. PSA is again 0 because we want to use the prescaler. PS012, we can select the 1:16 prescaler so that it is divided by 16. So what we can move in the T0 con register at a time is con will be equal to 110, and then the prescaler should be there, and then 0000. So this is the value we want to move to our timer 0 control register. Here TMR0 con is equal to 0B, and this, not TMR0 con, T0 con. So now our port is set as an output port, our timer is selected. So let's calculate with a prescaler of 16 how much time one timing cycle will consume. So the prescaler 16, this implies that one cycle will be equal to 16 microseconds. This implies that every count will take 16 microseconds. And how much delay do we need? Delay required is 300,000 microseconds or 0.3 seconds. So we will divide 300,000 by 16 and let's see what is the result. 18750. So this is equal to 18750. We will need this much counts to generate a delay of 0.3 seconds. So we will subtract this 18750 from that, and that will become 46786, and this will be this value will be preloaded to the timer 0, 46786, and then the timer will start counting up from this particular value. Let's go to the declaration of delay subroutine. So here I will declare an integer now. Integer preload, and here also I will declare the data type as integer preload. Okay, and here we will pass on what value? If we see here 46786, and let's make it rd0 is equal to rd0 not. So this is not required, and I can set rd0 is equal to 0 here. So now what is happening in our main loop is that we are setting the port as output, we are setting the configuration of our T0 con register, a prescaler of 16, we are clearing the output pin, and then we are continuously complementing the pin RD0 with a delay of 0.3 seconds. So how will this value give a delay of 0.3 seconds? We will write here, we will develop a logic in this loop, the delay loop. So let's start writing the program. What we want to do is we want to TMR0 is equal to preload. First we want to load this value, the 46786, into the timer 0 register. Now keep it in mind that when I write, don't write L or H postfix after TMR0, it will be read or written as a complete 16-bit register. So I don't have to divide this 16-bit number manually into two 8-bit portions and manually load it into the lower and higher registers. I don't have to do that, so that is very convenient. Then TMR0 on is equal to 1. Now we have turned on the timer, so now it will start counting up from whatever value was present already inside this register. There was 46786 inside this register, so it will start counting up from there, and up till where it will count? Up till 65536. And when, as soon as it overflows from 65536 to 0, the TMR0 IF bit will become 1. So what we can do here is while not TMR0 IF, wait here. This while command will keep the microprocessor waiting and will keep polling for this TMR0 IF flag, and until it is 0 it will wait, and as soon as it becomes 1 it will go to the next line, and here it will just turn off the timer. TMR0 on is equal to 0, and it will clear the flag TMR0 IF is equal to 0. So the flag is cleared, the timer is turned off, and then it will return. This program should blink this RD0 LED with a delay of 0.3 seconds. Let's compile it and see if it is working as expected or not. So the program has compiled successfully. Let's open our Proteus and let's simulate this. Okay, so this is your simulation. I have tried to set this time scale to precisely put the transition on one of these separations. So currently the time scale is showing 37.33 and we have 8 boxes for one transition. So 37.33 into 8 is around 299 point something. So that is 299 milliseconds delay, and that is not this time scale that I have set it manually. So this calculation is not very precise, but I am very confident that the calculations that we have done here will result in a very precise 300 millisecond delay. So let's try to change this value and let's try to see if we want to reduce our delay from 0.3 seconds to 0.03 seconds. So let's go back to the calculations. If we want 30,000 microseconds or 0.03 seconds and divide by 16, what is the result? That is 1875. So I will subtract this from 65536 and the result is 63661. So we will put 63661 here and we will clean and build our project once again. So now the build is successful and now we should have a delay of approximately 30 milliseconds. So let's see if it is working or not. So now if we see here, if we put it at 5 milliseconds, there should be 2, 3, 4, 5, 6 blocks. So it is precisely 30 milliseconds. And now you can see that there is not an error of even 1 millisecond in this approach. So how much better is this approach to create a delay using a timer as compared to what we were doing before using a for loop or using the nested loops in assembly language. So using timer to create a delay is very effective and very precise up to one count of this timer. We will use interrupts with timers in our next lecture. So in this lecture let's stop here, and you should try to use the timer in different modes, with prescaler on, without prescaler on. Change the prescaler value and delay and try to run your program to see whether your program is working fine and whether you are comfortable in using the timer peripheral or not. And once you have done that, in our next lecture we will get rid of this line where we are checking or polling the status of this timer 0 interrupt flag, or the status bit that is telling us whether the timer has overflowed or not, and we don't have to wait here. So we will assign the interrupt peripheral to check this bit for us in the background through hardware and then just inform us whenever this is full. So we'll do it in the next lecture. For this lecture we are done. Let's see you in our live session on Saturday inshallah, and please note down your queries related to the previous 3-4 lectures and I'll try to answer them in this session inshallah. And apart from the session, if you have any other questions, you can always post it in the respective week's channel on the Microsoft Teams. So have a very happy Eid, stay blessed, take care, Allah Hafiz.